Hi and welcome to this lecture on random variables introduction. To start off, let's consider the experiment of going to office with outcomes late, on time, and early. These outcomes can be defined based on arrival time. It's often useful to represent the outcomes by numbers. In this case, for instance, we want to develop a kind of rewarding mechanism. For late arrival, you would get a -1 point bonus. For on-time arrival, you get nothing. For early arrival, you get a plus bonus point. And this kind of transformation of the outcomes of a random experiment to numbers is done via a function whose domain is the sample space of the random experiment and whose range is a set of numbers. This is called, in probability theory, a random variable. In this case, x of late is -1, x of on time is 0, the value of x for early arrival is 1. Remember that these numbers can be defined differently based on what the problem is or what the example is. Then we repeat this experiment, for instance, 100 times and record the arrival time. Late 40 times, on time 10 times, and early 50 times. The relative frequency is obviously 0.4, 0.1, and 0.5 respectively. Then we can calculate the probability of x getting or taking a value of -1, which is the same as the probability of late arrival, which we already estimated to be 40%. Likewise, the probability of x taking 0 is 10%, and taking a value of 1 is 50%. And obviously, we can combine these events to generate secondary ones. For example, the probability that x is smaller or equal to 0. You know that when we say that x is smaller or equal to 0, there are two values for x included in this event, and that is the x equals to -1 and x equals to 0. Therefore, we add these two probabilities. 0.4 plus 0.1 is 0.5, which is 50%. Likewise, the probability of x bigger or equal to 0 includes these two events, x equals to 0 and x equals to 1. When we add the probability of the two, we get 60%. That is the probability that you get either no reward or a plus point. At 60%, the probability that you get no rewards or a negative reward is 50%. These are namely secondary events. Next, we consider the experiment of going to a bakery somewhere near where we live, and count the number of people in the queue waiting in front of us. And we repeat this for 100 times. Let's say 100 days or 100 times you go to the bakery, depending on how many times you go there per day. You observe no persons or no people waiting 4 times, 1 person 10 times, 2 persons waiting 20 times, 3 persons waiting 30 times, 4 persons waiting 21 times, 5 persons waiting 10 times, and more than 5 persons waiting in the queue 5 times. So you calculate the relative frequency, which is relatively easy, and then you can compute different probabilities using this random variable. So we define random variable n. This name can be anything else from S to B, where B contains the values 0, 1, 2, 3, 4, 5, or bigger than 5. Then the probability that you see nobody waiting or there's nobody waiting is 0.4 or 4%. Likewise, the probability of you having more than 5% waiting is 5%. Likewise, you can calculate the probability of 3, 1, 2, and so on. You can also calculate the probability of secondary ones. For example, the probability that 3 or less than 3 people are waiting. That would be a combination of 0, 1, 2, and 3. And you add the probabilities from the table in the previous slide, you get 64%. If you look at the set B is a set of numbers. So it can be discrete numbers like this set, like the example from the office arrival, it can also be continuous set. Depending on what B is, the random variable can be discrete or continuous. If B contains discrete values, such as this example here, then the random variable is discrete. If B contains continuous values, those are the values with decimal points, then the random variable is continuous. Then we use a function that would present the probability distribution of the random variable, and that's a function which is defined from B, which is the range of the random variable, to the interval 0 to 1, and this function is called PMF, or probability mass function, or probability density function, PDF. For example, for this bakery scenario, f of 0 is the probability that n equal to 0 is 0.04, and f of 1 is equal to the probability n is equal to 1 is 0.1, and so on and so forth. We can obviously plot the PDF of f. That means we can represent the probability of each one of them by a histogram, for example. That is the probability distribution of the random variable n. Next, consider the experiment of recording the time it takes you to arrive office. And suppose you run this experiment 100 times. That means you record the time that you need to arrive office in terms of seconds or minutes 100 times. First day you need 15 minutes, second day you need 14.5 minutes, third day you need 15.2 minutes, and so on and so forth. And if you look at this example, and if we define the random variable t from s to 0 infinity, then this range is starting from 0 and runs up to plus infinity, of course not included plus infinity. Theoretically, one wouldn't go, your office arrival time wouldn't go to infinity. In order for us to include all possible values, we just consider a very general form from 0 to plus infinity. Otherwise, your arrival time in terms of minutes to office should be bounded by some minutes. Nevertheless, this t, which is defined from s to 0 infinity, is a continuous random variable, as we defined earlier, because this 0 to infinity contains any number between 0 to infinity. And that's why this is a continuous set of numbers. Therefore, this random variable t, which is our time to arrive office, is a continuous random variable. When we calculate the probability of a particular time in terms of continuous random variable, it's nearly 0. The reason for that is that we have in a continuous interval infinitely many values, and if we want to calculate the probability of each value to occur, in fact we are dividing 1 by infinitely many values, and dividing 1 or any constant number by infinitely many values or by infinity gives us only 0. Therefore, in case of continuous random variables, calculation of the probability of every single value in the range is not making that much of sense, because this is anyway 0. In other words, for example, the probability that you arrive in 15.2 minutes to office is nearly 0. In order to overcome this problem, what we do is to calculate the probability of t taking values in certain interval. For example, what is the probability that we arrive, or we take 15 to 16 minutes in this interval time to arrive to office? And this probability calculation is done through probability density function. The expected values of the random variable is defined for discrete variables as the sum of xi, f of xi. Xi are values in set B, f of xi are the respective probabilities. For the continuous random variable, this is the definite integral x fx dx. If you consider the example of going to office, we can calculate the expected value as -1 times 40%, 0 times 10%, and 1 times 50% to get 0.1, and that is the expected value of the x random variable x if we run this experiment a large number of times and we follow the same trend. Likewise, we can calculate the variance of a random variable. For a discrete random variable, the variance is xi minus the mean. This mu is the mean or expected value squared times the probability, while in continuous case, this is x minus the mean all square times f of x. For example, if you want to calculate the variance of the random variable x for office arrival, and we have calculated the expected value earlier to be 0.1, then the variance would be minus 1, which is the first value, minus 0.1 all squared times 40%, which is this one, 0 minus 0.1 all squared times 0.1, which is 10%, this one here, and 1 minus 0.1 squared times 50%. If you do this calculation, you get 0.89, which is the variance of our random variable x in terms of office arrival. We can also calculate the standard deviation of our random variable by taking the square root of this variance. And that's valid also for the continuous case, where you calculate first the variance and then calculate the second root and you get the standard deviation.